Your existence required the death of multiple massive stars. Not metaphorically, literally. The carbon in your DNA, the nitrogen in your proteins, and the phosphorus in your cell membranes could only exist because these stellar giants exploded billions of years ago in exactly the right sequence. New 2025 studies confirm each essential element's formation depended on very specific stellar conditions. The phosphorus that powers every cell in your body forms only during the final seconds of certain dying stars. The implications of what researchers have discovered will change how you think about being alive. To understand this cosmic connection, we need to trace the manufacturing process that created you. The journey begins at the most advanced observatories on Earth, where scientists monitor the stellar factories that forge the elements of life. The Stellar Assembly Line of Life. ALMA's network of giant dish antennas captures the faint radio signals from stellar cores, where temperatures reach 100 million degrees and atoms transform into the building blocks of life. These instruments reveal how the universe operates as a vast manufacturing system, creating the elements essential for biological chemistry through processes that span billions of years. Recent ALMA observations show something remarkable about cosmic manufacturing. Star formation across the observable universe has slowed dramatically over the past 5 billion years, with current measurements indicating that most of the cosmic assembly line still lies ahead of us. The universe has barely begun creating the heavy elements necessary for complex chemistry. Inside stellar cores, different-sized stars operate as specialized factories. Stars 8 times more massive than our Sun reach core temperatures of 3 billion degrees, where carbon atoms form through the triple alpha process. 3 helium nuclei collide in rapid succession, creating carbon-12, the backbone of organic chemistry. Stars between 8 and 25 solar masses continue the assembly line, fusing elements in concentric shells around an iron core. The timing of these nuclear reactions follows precise sequences that determine which elements can exist. But phosphorus presents the most challenging manufacturing requirement of all. This essential component of DNA and cellular energy systems demonstrates just how extraordinary stellar chemistry becomes. Phosphorus can only form in stars between 15 and 25 solar masses during explosive silicon burning that lasts mere seconds before core collapse. The narrow mass range and brief production window make phosphorus the scarcest biological element in the universe. When massive stars exhaust their nuclear fuel, gravitational collapse triggers explosions that distribute their manufactured elements across space. Type II supernovae from stars above 25 solar masses release carbon, nitrogen, oxygen, and phosphorus in characteristic ratios. These explosions inject fresh, heavy elements into surrounding gas clouds at velocities exceeding 10,000 kilometers per second, spreading them across hundreds of light years. Type Ia supernovae contribute a different elemental cocktail to cosmic chemistry. These explosions occur when white dwarf stars accumulate matter from companion stars until they reach a critical mass threshold. The resulting detonation produces large quantities of iron, nickel, and cobalt, while creating smaller amounts of the lighter biological elements. This dual supernova system ensures that interstellar space receives both the structural elements for rocky planets and the transition metals needed for complex biochemistry. Spectroscopic analysis reveals dramatic metallicity gradients across spiral galaxies. The central regions contain 3 times more heavy elements than outer spiral arms, creating zones where planetary systems inherit vastly different chemical inventories. Our solar system formed in a galactic sweet spot, where multiple generations of both supernova types had enriched the local environment to optimal levels for biological chemistry. The Milky Way's chemical evolution spans 13 billion years of stellar processing. First-generation stars contained only hydrogen and helium, making planets and life impossible. These primordial giants lived brief lives before exploding and seeding space with the first heavy elements. Second-generation stars incorporated this enriched material, continuing the manufacturing process and producing more diverse chemistry upon their deaths. Our Sun represents a third-generation star born from gas clouds already enriched by billions of years of stellar processing. Isotope analysis of meteorites shows that our solar system's formation incorporated material from at least 50 different supernovae explosions. Each contributed specific elements in characteristic ratios, creating the precise mixture needed for terrestrial planets and biological chemistry. The chemical signatures in stellar spectra tell the story of galactic enrichment over cosmic time. Stars formed 12 billion years ago show metal abundances 1/100th of solar values. 8 billion-year-old stars contain 1/10 the heavy element content of our Sun. This steady increase in metallicity created an expanding galactic zone where planets could form with sufficient heavy elements to support complex chemistry. Stellar winds from massive stars also contribute to element distribution between explosive events. These continuous streams of particles carry newly synthesized elements into surrounding space at gentler velocities than supernova shockwaves. Wolf-Rayet stars lose up to one solar mass every million years through powerful winds enriched with carbon, nitrogen, and oxygen from their exposed stellar cores. The interaction between stellar winds and supernova explosions creates complex mixing patterns in interstellar space. Computer simulations show how multiple stellar generations work together to homogenize element abundances across galactic regions. This mixing process ensures that when new stars form, they incorporate representative samples of all previous stellar nucleosynthesis. ALMA observations track this ongoing process by monitoring molecular clouds where the next generation of stars will form. These dense regions already contain water, carbon monoxide, and dozens of other molecules built from stellar-manufactured atoms. The chemical complexity increases in regions that have experienced recent supernova activity, showing how stellar death directly enables the formation of complex molecules needed for life. Modern stellar archaeology techniques allow astronomers to trace individual stars back to their birth environments and identify which ancient supernovae contributed their atoms. The European Space Agency's Gaia mission has mapped the positions and chemical compositions of over 1 billion stars, revealing how element abundances vary across different stellar populations and galactic regions. The stellar assembly line continues operating throughout the observable universe, but its productivity has peaked. Current star formation rates suggest that galaxy-wide chemical enrichment will plateau within the next few billion years as available gas supplies become depleted. This makes our current epoch special in cosmic history. We exist during the most productive period of biological element synthesis. Each atom in your body carries the fingerprint of stellar nuclear processes that occurred across billions of years of cosmic time. The oxygen you breathe formed in stellar cores 20 times more massive than our Sun. The calcium in your bones crystallized from gas clouds enriched by hundreds of ancient supernovae. But the stellar connection to life extends far beyond the atoms themselves. The same explosive events that created your elements also launched invisible messengers across the galaxy, carrying information and energy that continues to influence biological processes in ways scientists are only beginning to understand. Cosmic radiation, the universe's hidden influence. These invisible messengers reach Earth through the most sophisticated detection systems ever built. Deep within Antarctica's frozen landscape sits the Ice Cube Nutrino Observatory, where scientists track particles that pass through the entire planet undetected. The facility consists of 5,000 digital optical modules suspended throughout a cubic kilometer of ice, capturing brief flashes of blue light when high-energy neutrinos interact with ice molecules. The 2025 data from Ice Cube has identified specific supernova remnants as sources of the highest energy cosmic ray particles reaching Earth. These discoveries reveal that stellar explosions continue influencing planetary environments long after their visible light fades. Multi-messenger astronomy now combines neutrino observatories with gravitational wave detectors and traditional telescopes to create complete pictures of how massive stellar deaths accelerate particles across the galaxy. Cosmic rays transport far more than energy across interstellar space. High-energy particles carry complex organic molecules attached to interstellar dust grains across distances spanning hundreds of light years. Amino acid precursors and simple sugars survive these journeys by binding to carbon-rich dust particles that shield them from destructive ultraviolet radiation. These molecules arrive in stellar nurseries where new planetary systems form, seeding them with preformed biological building blocks. Our solar system's journey through the Milky Way exposes Earth to dramatically varying cosmic ray intensities. As we orbit the galactic center every 225 million years, we pass through spiral arms where recent supernovae have enriched the local environment with high-energy particles. Current measurements show cosmic ray flux increases by 30% when our solar system travels through these active star-forming regions compared to quieter spaces between spiral arms. Ice core samples from Greenland and Antarctica preserve records of cosmic ray intensity fluctuations over the past 800,000 years. These data reveal clear correlations between cosmic ray bombardment and major climate transitions throughout Earth's history. Periods of increased cosmic ray exposure correspond to ice age cycles, suggesting that stellar explosions in our galactic neighborhood directly influence planetary climate systems over geological timescales. When cosmic ray particles enter Earth's atmosphere, they create cascades of secondary particles that penetrate to ground level. A single high-energy proton from space generates showers containing millions of muons, electrons, and photons that spread across several square kilometers. These particle showers continuously bombard every living organism on the planet's surface. The average human body experiences several cosmic ray interactions every second, with particles passing through cellular structures and occasionally damaging DNA molecules. Lightning formation depends heavily on cosmic ray ionization of atmospheric gases. High-energy particles create pathways of charged atoms that provide initial channels for electrical discharge between clouds and ground. Regions with higher cosmic ray flux experience increased lightning activity, which drives atmospheric chemistry reactions that produce nitrogen compounds essential for plant growth. Global lightning frequency varies with cosmic ray intensity, creating connections between distant stellar explosions and agricultural productivity on Earth. The 2025 research from the CERN Cloud Experiment demonstrates that cosmic rays create condensation nuclei necessary for cloud formation in Earth's atmosphere. High-energy particles ionize water vapor and atmospheric gases, generating microscopic particles around which water droplets form. Variations in cosmic ray intensity directly affect global cloud cover, which regulates planetary temperature through changes in solar radiation reflection. Cosmic ray flux measurements show 22% variations that follow our solar system's vertical oscillations above and below the galactic plane. When we travel through regions with higher stellar density, increased supernova activity boosts local cosmic ray levels. These oscillations occur over periods of 30 to 40 million years, matching timescales of major mass extinction events in Earth's fossil record. The correlation suggests that our planet's biological history reflects the rhythm of our journey through galactic space. Atmospheric chemistry models reveal that cosmic rays drive the formation of hydroxyl radicals that control the breakdown of greenhouse gases like methane. Higher cosmic ray intensity accelerates methane destruction in the upper atmosphere, reducing its warming effect on global climate. This process creates feedback loops where stellar activity in distant parts of the galaxy influences Earth's atmospheric composition and surface temperature. Biological research demonstrates that cosmic ray exposure influences cellular repair mechanisms across all life forms. Organisms in high-altitude environments show enhanced DNA repair capabilities compared to sea-level populations, suggesting evolutionary responses to increased cosmic radiation. The repair systems appear optimized for the specific types of genetic damage caused by cosmic ray interactions, indicating that stellar radiation has shaped biological evolution at the molecular level. Modern satellite networks monitor cosmic ray intensity in real time, revealing how solar activity modulates the interstellar radiation reaching Earth's atmosphere. During periods of high solar wind activity, our star's magnetic field deflects low-energy cosmic rays, reducing their flux by up to 50%. This solar shielding effect varies with the 11-year solar cycle, creating regular fluctuations in cosmic ray exposure that correlate with changes in atmospheric chemistry and climate patterns. The discovery that cosmic rays carry organic molecules across interstellar distances fundamentally changes our understanding of how biological chemistry develops throughout the galaxy. Complex carbon compounds survive journeys lasting millions of years, while attached to dust grains accelerated by supernova shockwaves. These molecules arrive at stellar nurseries chemically intact, providing shortcuts for the development of biological systems on newly formed planets. Space-based detectors reveal that the highest energy cosmic rays originate from stellar explosions occurring within our galactic cluster, rather than from distant galaxies. Every breath we take occurs while high-energy messengers from ancient stellar explosions pass through our bodies, connecting us directly to the explosive deaths of massive stars. But these cosmic messengers represent only part of the stellar influence on biological chemistry. The space between stars harbors its own chemical secrets, where temperatures near absolute zero hide surprising molecular complexity. The molecular factories between stars. At the Space Telescope Science Institute in Baltimore, astronomers sit before massive screens displaying infrared images that reveal the chemical secrets hidden in the emptiness between stars. The James Webb Space Telescope operates 24 hours a day, collecting light from molecules floating in regions so cold and empty that they seemed lifeless until recently. These infrared signatures tell a different story about interstellar space than anyone expected. The observatory's instruments detect molecular fingerprints across wavelengths invisible to human eyes. Each molecule absorbs and emits infrared light at characteristic frequencies, creating spectral lines that identify specific compounds scattered throughout the galaxy. Water molecules appear as distinctive peaks at 6.2 micrometers. Methanol shows up at 9.7 micrometers. Carbon dioxide creates sharp absorption features at 15.2 micrometers. The telescope catalogs these signatures automatically, building databases of cosmic chemistry that grow larger each day. Scientists working with 2025 JWSD data have confirmed the presence of over 300 different organic compounds drifting through interstellar space. These molecules include formamide, acetaldehyde, and glycolaldehyde direct precursors to amino acids and sugars. The abundance surprised researchers who previously assumed that complex chemistry required planetary surfaces or stellar atmospheres. Instead, the vacuum between stars hosts an active molecular laboratory operating on scales spanning hundreds of light years. Molecular clouds represent the most chemically active regions in interstellar space, despite temperatures that drop to within 10 degrees of absolute zero. These dense accumulations of gas and dust contain enough material to form thousands of stars, yet they remain stable for millions of years before gravitational collapse begins. Inside these frigid environments, Molecules that would decompose instantly at room temperature persist for geological timescales, while participating in slow chemical reactions. The Orion Nebula contains molecular clouds where temperatures reach 4 Kelvin cold enough to freeze nitrogen solid, yet spectroscopic analysis reveals dozens of organic compounds forming continuously. Hydrogen sulfide reacts with carbon monoxide to produce complex sulfur-bearing molecules. Ammonia combines with formaldehyde to create methylamine, a compound found in living cells. These reactions proceed through quantum tunneling effects that allow atoms to cross energy barriers impossible at higher temperatures. Cosmic rays penetrate these dense clouds and provide the energy needed to break chemical bonds and create reactive molecular fragments. When high-energy protons strike ammonia molecules, they knock off hydrogen atoms that immediately react with nearby carbon monoxide. The process creates formamide, which serves as a precursor to nucleotide bases found in RNA. Similar cosmic ray interactions convert simple alcohols into aldehydes that participate in sugar formation, pathways identical to biological processes. Interstellar dust grains function as microscopic reaction vessels where prebiotic chemistry occurs. These particles measure less than 1 micrometer across, but provide surfaces where gas-phase molecules can stick and interact. Silicon-rich grains attract water molecules that freeze into thin ice mantles. Carbon-rich grains collect organic vapors that condense into complex molecular films. Each grain operates as an individual chemical laboratory with its own unique reaction environment. The ice mantles surrounding dust grains create surprisingly complex reaction networks. Water molecules form the foundation layer, followed by methanol, formaldehyde, and carbon monoxide that freeze in successive layers as temperatures drop. Cosmic ray bombardment provides energy to break bonds within these ices, creating mobile radicals that migrate across grain surfaces and combine into larger molecules. Laboratory experiments reproducing these conditions generate amino acids, fatty acids, and even nucleotide components from simple starting materials. Grain surface reactions follow pathways that mirror biochemical processes found in living cells. Hydrogen atoms landing on icy surfaces react with carbon dioxide to form formic acid, then methanol, then more complex alcohols. These alcohols interact with ammonia-rich regions to produce amines and amides. The sequential addition of carbon atoms builds molecular chains identical to those found in meteorites and cometary samples. The similarity suggests that life's chemical foundations form naturally, wherever the right conditions exist. Stellar winds from massive stars carry these molecular building blocks across interstellar distances measured in thousands of light years. Young hot stars emit powerful particle streams that sweep up surrounding dust and gas, accelerating them to velocities exceeding 1,000 kilometers per second. The winds create expanding bubbles of enriched material that merge with other stellar outflows, mixing and distributing organic molecules throughout galactic regions where new star formation occurs. Supernova explosions inject additional energy into molecular cloud chemistry, while dispersing heavy elements needed for complex molecule formation. The shockwaves heat dust grains enough to sublimate their ice mantles, releasing stored organic compounds into the gas phase where they can react with freshly synthesized metals. Iron and magnesium atoms expelled by supernovae catalyze reactions that would otherwise proceed too slowly to matter. The combination creates chemical environments more diverse than any terrestrial laboratory. Research published in 2025 demonstrates clear correlations between cosmic ray flux and molecular complexity in different galactic regions. Areas with higher supernova rates show increased abundances of nitrogen-bearing organic compounds. Regions near active star-forming complexes contain more diverse molecular inventories than quieter galactic locations. The patterns suggest that stellar activity drives chemical evolution in interstellar space, just as it creates the heavy elements needed for planet formation. Radio telescope observations track how molecular complexity spreads across galactic scales through stellar feedback processes. Giant molecular cloud complexes span hundreds of light years and contain enough organic material to supply millions of planetary systems with performed biological building blocks. These complexes fragment under gravitational instabilities, creating smaller clouds that eventually collapse to form new stellar nurseries where planets inherit their chemical legacy. The universe functions as a chemical manufacturing system that operates independently of planetary surfaces or biological processes. Interstellar space contains all the molecular diversity needed to jumpstart biological chemistry on any world with suitable physical conditions. The continuous production and galactic distribution of organic compounds ensures that life's chemical foundations exist wherever planets form from chemically enriched stellar nurseries. These molecular factories between stars prepare the raw materials that will eventually become incorporated into planetary systems during their formation, carrying with them the accumulated chemical complexity of billions of years of cosmic evolution. Stellar nurseries and planetary inheritance. On the high plateau of Chile's Atacama Desert stands the European Southern Observatory, home to some of the most powerful telescopes ever built. Here scientists point their instruments towards stellar nurseries, where new planetary systems emerge from the remnants of ancient stars. The Very Large Telescope Array consists of 4 massive mirrors working together to capture light from protoplanetary disks thousands of light years away. These spinning disks of gas and dust represent the birthplaces of planets, and their chemical composition determines what types of worlds will eventually form. The observatory's sphere instrument reveals protoplanetary disks in unprecedented detail. These structures span distances larger than our entire solar system, yet contain intricate patterns of rings, gaps, and spiral arms carved by forming planets. Each disk preserves the chemical fingerprint of its parent molecular cloud, carrying forward the accumulated products of stellar nucleosynthesis spanning billions of years. When astronomers analyze the spectral signatures from these disks, they discover not just simple elements but complex organic molecules inherited directly from interstellar space. Recent 2025 observations show that planet formation begins while parent stars are still actively accumulating mass from their surrounding disks. This simultaneous process means that forming planets incorporate material that reflects both the original molecular cloud composition and the ongoing nuclear reactions in their central star. The timing creates planetary systems with chemical inventories that vary dramatically depending on when and where individual planets condense from the swirling disk material. The HL Tauri system provides the most detailed view of this inheritance process. Located 450 light-years away in the constellation Taurus, this young star system shows multiple gaps in its protoplanetary disk where planets are actively forming. Spectroscopic analysis reveals that the disk contains water vapor, carbon monoxide, hydrogen cyanide, and dozens of other molecules originally synthesized in interstellar space. These compounds become incorporated into the solid materials that build planetary cores, atmospheres, and surface compositions. The disk structure around HL Tauri demonstrates how chemical complexity varies with distance from the central star. The innermost regions contain refractory materials like aluminum oxide and calcium-aluminum inclusions that condense at temperatures exceeding 1500 Kelvin. Moving outward, silicate dust grains dominate the warm disk regions where terrestrial planets form. Beyond the snow line at approximately 3 astronomical units, water ice coats dust particles, creating the foundation for giant planet cores. Each ring visible in the HL Tauri disk represents a different chemical environment where specific types of planetary building blocks accumulate. The gaps between rings show where forming planets have gravitationally cleared their orbital paths while continuing to accrete material. Radio observations reveal that organic molecules concentrate in the cooler outer disk regions, creating reservoirs of prebiotic chemistry that will eventually be incorporated into comets and outer planetary system objects. The chemical gradients observed in HL Tauri match theoretical predictions for how stellar material becomes organized during planetary system formation. Heavy elements settle toward the disk midplane, while lighter gases remain suspended in the upper atmosphere. Turbulent mixing redistributes materials radially, ensuring that planets forming at different distances inherit diverse chemical compositions. The process creates worlds with unique elemental fingerprints that reflect their specific formation environments. Protoplanetary disk chemistry varies dramatically based on the parent star's galactic environment and formation history. Stars born in the galactic center regions inherit material enriched by thousands of previous stellar generations. These metal-rich environments produce planetary systems with higher abundances of heavy elements essential for rocky planet formation and complex chemistry. Systems forming in outer galactic regions contain fewer heavy elements, limiting their potential for terrestrial planet development. Stellar metallicity measurements show direct correlations between heavy element abundance and planetary system architecture. Stars with metal content twice that of our Sun typically host multiple rocky planets in their inner regions. Stars with half-solar metallicity rarely produce terrestrial worlds larger than Mars. The relationship demonstrates that successful planet formation requires specific chemical conditions inherited from previous generations of stellar evolution. Computer simulations reveal how gravitational interactions during planet formation distribute life-enabling materials throughout developing solar systems. As planetary embryos collide and merge, they mix materials originally condensed at different distances from their parent star. This process delivers water-rich asteroids to the inner system, while scattering organic-rich comets throughout the outer planetary region. The gravitational choreography ensures that terrestrial planets receive diverse chemical inventories from across their entire solar system. The late heavy bombardment period between 4.1 and 3.8 billion years ago delivered not just water but complex organic molecules to early Earth through asteroid and comet impacts. Chemical analysis of ancient zircon crystals shows that Earth's oceans contained amino acids and other prebiotic compounds within 200 million years of the bombardment's end. The rapid appearance of chemical complexity suggests that impact delivery provided ready-made ingredients for early biological processes. Comet compositions reveal the outer solar system's preservation of interstellar organic chemistry. The Stardust mission collected particles from Comet Wild 2 that contain glycine, the simplest amino acid found in proteins. The 67P/Churyumov-Gerasimenko comet studied by the Rosetta spacecraft shows abundant organic compounds including formamide and acetone. These discoveries prove that the cold outer regions of planetary systems maintain chemical libraries inherited from their parent molecular clouds. The chemical diversity available to forming planets depends on their parent star's galactic environment and formation history. Systems born from molecular clouds, enriched by recent supernova activity, inherit more complex chemical inventories than those forming from relatively pristine gas. The timing of stellar birth within galactic chemical evolution determines the raw materials available for planet formation and eventual biological development. Every rocky planet carries within its structure the accumulated chemical legacy of multiple stellar generations. The iron in planetary cores formed in massive stars that exploded billions of years ago. The silicon in crustal rocks crystallized from stellar wind material expelled by intermediate mass stars. The carbon in atmospheric gases originated in the nuclear furnaces of ancient red giants. This elemental inheritance connects every world to the broader history of cosmic chemical evolution, creating countless laboratories where stellar material transforms into the conditions necessary for life. The exoplanet revolution and cosmic habitability. These planetary laboratories now number in the thousands as astronomical surveys reveal worlds orbiting stars throughout our galactic neighborhood. Each confirmed exoplanet carries chemical fingerprints inherited from its host star during formation. Spectroscopic measurements reveal direct correlations between stellar metallicity and planetary system architecture. Stars containing twice the heavy element abundance of our Sun typically host multiple terrestrial planets with diverse chemical compositions. Low metallicity stars rarely produce rocky worlds larger than Mars, because insufficient solid material exists in their protoplanetary disks to build substantial planetary cores. The connection between stellar chemistry and planetary habitability extends beyond simple element abundance ratios. Metal-rich stars provide the raw materials needed for continental crust formation, magnetic field generation, and atmospheric chemistry that supports complex biochemical processes. Planets orbiting these chemically enriched stars inherit larger inventories of phosphorus, sulfur, and trace elements essential for biological metabolism. The relationship demonstrates that successful biosphere development requires specific stellar chemical conditions accumulated over billions of years of galactic evolution. Stellar age creates additional constraints on long-term planetary habitability beyond initial chemical inheritance. Young stars exhibit violent flare activity that strips planetary atmospheres through intense ultraviolet radiation and particle bombardment. Middle-aged stars like our Sun provide stable energy output over geological timescales, allowing atmospheric chemistry to reach equilibrium states compatible with biological processes. Ancient stars begin depleting their nuclear fuel supplies, gradually increasing luminosity until surface temperatures on their planets exceed the limits for liquid water. The main sequence lifetime of different stellar types determines the available time for biological evolution to occur on orbiting planets. M-dwarf stars burn hydrogen so slowly that they remain stable for trillions of years, providing ample time for complex life to develop despite initial atmospheric challenges. G-type stars like our Sun maintain habitable conditions for approximately 10 billion years before expanding into red giants that sterilize their planetary systems. Massive O and B stars exhaust their fuel within millions of years, insufficient time for biological evolution beyond simple cellular forms. Red dwarf stars present unique chemical environments that could support biological processes fundamentally different from those on Earth. These cool stars emit primarily infrared radiation that penetrates deeper into atmospheric layers than visible light. Planets receiving this long-wavelength energy develop atmospheric chemistry dominated by photochemical reactions involving complex organic molecules rather than simple water photolysis. The resulting chemical networks could support metabolism based on different energy storage compounds than those used by terrestrial life. Stellar activity patterns influence planetary atmospheric retention through magnetic field interactions and particle wind effects. Stars with strong magnetic fields generate powerful stellar winds that can either strip planetary atmospheres or compress them, depending on the planet's own magnetic shielding capabilities. Planets orbiting magnetically active stars show enhanced atmospheric escape rates for light elements, while retaining heavier compounds that could support alternative biochemical pathways. The discovery of SBCULOS-3b demonstrates how tidally locked exoplanets around red dwarf stars might harbor unexpected chemical environments. This world maintains permanent day and night hemispheres with extreme temperature gradient that drive continuous atmospheric circulation patterns. The day side reaches temperatures hot enough to vaporize silicate rocks, while the night side remains cold enough to condense complex organic molecules from atmospheric gases. This creates dynamic chemistry zones, where materials cycle between different chemical states as atmospheric currents transport them around the planet. Gliese 12b represents another example of exoplanet atmospheric analysis, revealing active chemistry independent of biological processes. Located just 40 light-years away, this Earth-sized world receives stellar radiation levels that could maintain liquid water on its surface. Preliminary atmospheric analysis suggests the presence of water vapor, carbon dioxide, and trace organic compounds consistent with chemical inheritance from its formation environment, rather than biological activity. The James Webb Space Telescope has revolutionized exoplanet atmospheric analysis by detecting molecular signatures in worlds hundreds of light-years distant. The observatory identifies specific compounds by measuring how starlight filters through exoplanet atmospheres during transit events. Water vapor shows characteristic absorption features at 1.4 micrometers. Carbon dioxide appears at 2 micrometers. Methane creates distinct signatures at 3.3 micrometers. Each detection provides information about planetary chemistry and potential habitability conditions. Recent 2025 atmospheric surveys reveal biosignature gases in several exoplanet atmospheres that suggest active chemical processing rather than biological activity. Oxygen and ozone detections in hot Jupiter atmospheres result from water vapor photolysis rather than photosynthesis. Phosphine signatures in Venus-like worlds indicate volcanic outgassing rather than biological production. These discoveries demonstrate that distinguishing between biological and non-biological sources requires detailed understanding of planetary chemistry and stellar influence. Different stellar spectral types create distinct photochemical environments that influence the types of atmospheric chemistry possible on their planets. K-dwarf stars emit balanced visible and infrared radiation that promotes diverse organic molecule formation in planetary atmospheres. M-dwarf stars provide primarily infrared energy that favors different chemical reaction networks involving longer wavelength photochemistry. F-type stars emit excess ultraviolet radiation that drives atmospheric chemistry towards simpler molecular forms through enhanced photodissociation rates. The galactic distribution of metal-rich stars creates zones where terrestrial planet formation occurs more frequently than in chemically primitive regions. The inner galaxy contains stellar populations with heavy element abundances 3 times higher than solar values, enabling robust rocky planet development. Outer galactic regions show reduced metallicity that limits terrestrial planet formation to smaller worlds with restricted chemical diversity. This spatial variation suggests that complex biological chemistry develops preferentially in specific galactic environments where stellar nucleosynthesis has progressed sufficiently. Statistical analysis of exoplanet discoveries reveals that the universe contains countless worlds where stellar material has transformed into planetary chemical systems capable of supporting biological processes. Every confirmed detection represents one example from populations numbering in the billions throughout our galaxy. These discoveries raise fundamental questions about our own solar system's chemical heritage and the specific stellar events that created the elements we find on Earth today. Galactic archaeology and our stellar ancestry. Scientists now trace these chemical histories through the most ambitious stellar census ever undertaken. The Gaia space mission operates from a control center in Darmstadt, Germany, where astronomers monitor data streams from humanity's most detailed galactic survey. The spacecraft orbits the Sun at a gravitational balance point 1.5 million kilometers from Earth, scanning the entire sky with instruments precise enough to measure stellar positions within microarcseconds. This accuracy equals detecting a coin on the Moon's surface from Earth. The mission maps over 1 billion stars simultaneously, recording their positions, distances, velocities, and chemical compositions to create the most detailed portrait of our galaxy ever assembled. Each star carries chemical fingerprints that reveal its birth environment and evolutionary history. Gaia's spectrometers analyze starlight across multiple wavelengths to determine elemental abundances with unprecedented precision. Iron absorption lines at 5270 angstroms indicate how much stellar material came from previous supernovae. Calcium signatures at 4226 angstroms reflect contributions from massive star explosions. Magnesium features at 5183 angstroms trace the influence of intermediate mass stellar deaths. These spectral signatures function like genetic codes that connect individual stars to specific ancient stellar events. The 2025 Gaia data release contains chemical analysis for over 30 million stars distributed throughout the Milky Way's disk and halo regions. This information allows astronomers to trace the precise stellar origins of elements found in our solar system through chemical archaeology techniques. Scientists compare the elemental ratios in our Sun with those of stars formed in different galactic environments and epochs. The matches reveal which stellar populations contributed material to the molecular cloud that eventually collapsed to form our solar system 4.5 billion years ago. Stellar archaeology identifies the specific types of ancient stars that contributed to Earth's composition by analyzing isotope ratios preserved in primitive meteorites. The Murchison meteorite contains presolar silicon carbide grains with isotopic compositions matching theoretical models for asymptotic giant branch star ejecta, along with amino acids that survived from interstellar space. These microscopic inclusions survive the violent processes of planetary formation to preserve records of specific stellar death events that occurred billions of years ago, providing direct evidence for individual stellar contributions to early solar system material. Our solar system's current location in the galaxy has exposed it to material from multiple distinct stellar populations throughout cosmic history. The Sun orbits the galactic center every 225 million years, while oscillating above and below the galactic plane with a period of 33 million years. This complex orbital motion carries our solar system through regions containing different chemical environments created by varying rates of star formation and stellar death. Each passage through spiral arms exposes us to material enriched by recent massive star explosions. Galactic chemical evolution creates systematic gradients of element abundance that influence habitability prospects across different regions of the Milky Way. The inner galaxy shows metallicity levels 3 times higher than our solar neighborhood due to enhanced star formation rates and supernova frequency. These metal-rich regions favor the formation of terrestrial planets with diverse chemical inventories suitable for complex biochemistry. Outer galactic regions contain insufficient heavy elements for robust rocky planet formation, limiting the development of solid surfaces where biological processes can occur. Stellar migration plays a crucial role in mixing and distributing heavy elements throughout galactic disks over billion-year timescales. Gravitational interactions with spiral density waves cause stars to drift radially across galactic regions, carrying their chemical compositions to new environments. This mixing process homogenizes element distributions that would otherwise remain segregated based on local star formation history. The migration also explains why some stars show chemical abundances inconsistent with their current galactic positions. Evidence indicates that our Sun formed in a different part of the galaxy and migrated to its current position through gravitational interactions with spiral structure. Chemical analysis shows our Sun contains higher alpha element ratios than typical for stars currently located at our galactic radius. These abundance patterns match those expected for stars born closer to the galactic center, where massive star formation rates remain elevated. Orbital integration models suggest our Sun originated approximately 2 kiloparsecs closer to the galactic center before migrating outward to its present location. The technique of chemical tagging allows astronomers to identify stellar siblings born from the same molecular cloud, despite their current separation across thousands of light years. Stars formed together retain nearly identical chemical compositions, even after gravitational interactions scatter them throughout the galaxy. By comparing detailed abundance patterns for multiple elements, scientists can reconstruct stellar birth associations and trace the dispersal of chemically related stars over galactic evolution timescales. Gaia observations reveal that the Milky Way contains numerous stellar streams created by the tidal disruption of smaller satellite galaxies. These streams preserve distinct chemical signatures from their parent systems, creating fossil records of ancient merger events. The Sagittarius stream shows element abundance patterns characteristic of dwarf galaxy nucleosynthesis environments. Material from these disrupted systems becomes incorporated into subsequent star formation, adding chemical diversity to the galactic mix available for planetary formation. We can trace our atomic heritage back to specific stellar events that occurred across cosmic time through increasingly sophisticated chemical modeling techniques. The carbon in our bodies formed in red giant stars that expelled their outer layers as planetary nebulae 8 to 10 billion years ago. The oxygen we breathe crystallized in massive star cores that exploded as supernovae 6 to 8 billion years ago. The calcium in our bones originated in type Ia supernova explosions, occurring 4 to 6 billion years ago within our galactic neighborhood. Every atom in your body carries an address that connects it to a specific location and time in galactic history, when stellar nucleosynthesis created it from simpler elements. This chemical archaeology reveals that we are not just made of star stuff, but represent a precise mixture of material from hundreds of individual stellar death events that occurred across billions of years of cosmic evolution. Our existence required the coordinated contributions from multiple stellar populations scattered throughout the ancient Milky Way. But the stellar influence on life extends far beyond the atoms themselves. The same explosive events that forged our elements continue sending invisible messengers across the galaxy that directly interact with biological processes on Earth. Cosmic rays and biological evolution. High-energy particles from these stellar explosions continuously bombard our planet, creating an invisible evolutionary force that has shaped life throughout Earth's history. Across the vast pampas grasslands of Argentina stands the Pier Auger Observatory, the largest cosmic ray detection facility ever constructed. This installation covers 3,000 square kilometers with 1,600 particle detectors arranged in a precise hexagonal grid. Each detector consists of a tank filled with purified water that produces flashes of blue light when cosmic ray particles pass through. 4 fluorescence telescopes scan the night sky, watching for the faint glows that appear when the highest energy particles in the universe collide with Earth's atmosphere. The observatory tracks cosmic ray events that carry energies exceeding 10 to the 20th electron volts, particles accelerated to velocities approaching the speed of light by stellar explosion occurring thousands of light years away. When these particles strike atmospheric molecules 30 kilometers above ground, they create cascades containing billions of secondary particles that spread across areas larger than major cities. The detection arrays record the arrival times and intensities of these particle showers with nanosecond precision, allowing scientists to trace each cosmic ray back to its point of origin in distant space. Research conducted throughout 2025 reveals that cosmic rays function as active drivers of genetic mutation and evolutionary change, rather than passive background radiation. High-energy particles penetrate living tissue and interact directly with DNA molecules, creating breaks in the double helix structure that cellular repair mechanisms must address. Most damage gets corrected accurately, but occasional errors during repair introduce genetic variations that natural selection can either eliminate or preserve. This process operates continuously throughout every organism's lifetime, generating the raw material for evolutionary adaptation. The intensity of cosmic ray bombardment varies dramatically based on our solar system's position within the galactic disk and our journey through different stellar environments. Current measurements show cosmic ray flux increases by 40% when Earth passes through spiral arm regions compared to the quieter interarm spaces. These variations occur over timescales ranging from millions to hundreds of millions of years, as our solar system completes its orbit around the galactic center, while oscillating above and below the galactic plane. Passage through spiral arms exposes Earth to enhanced cosmic radiation from multiple sources, including recent supernova explosions, active star formation regions, and interactions with giant molecular cloud complexes. The increased particle bombardment creates elevated mutation rates in all living organisms during these galactic transits. Fossil evidence shows that several major evolutionary transitions coincide with periods when our solar system moved through spiral arm regions, suggesting that cosmic ray exposure may have accelerated biological innovation. The Cambrian explosion 540 million years ago provides the most compelling example of this cosmic evolutionary connection. This remarkable period saw the sudden appearance of diverse animal body plans with complex organ systems, occurring during a time of enhanced cosmic ray exposure, as our solar system passed through an active star-forming region. The elevated mutation rates from increased stellar radiation may have provided the genetic variation necessary for rapid morphological innovation that characterizes this evolutionary milestone. Recent evidence suggests that specific mass extinction events may have been triggered by nearby supernova explosions that flooded our solar system with lethal doses of cosmic radiation. Geological deposits from the late Devonian extinction, 375 million years ago, contain elevated levels of iron-60 and plutonium-244, isotopes that form only in massive stellar explosions. These radioactive signatures indicate that supernova events occurring within 100 light-years of Earth may have delivered cosmic ray intensities thousands of times higher than current background levels. DNA repair mechanisms show clear evolutionary adaptations to cosmic ray damage patterns, indicating that stellar radiation has shaped biological systems at the molecular level. Organisms living at high altitudes where cosmic ray intensity increases show enhanced repair capabilities compared to sea-level populations. These repair systems target specific types of genetic damage characteristic of cosmic ray interactions, demonstrating that life has evolved molecular machinery optimized for countering stellar radiation effects. Earth's magnetic field plays a crucial role in modulating cosmic ray exposure and its biological effects by deflecting lower-energy particles toward polar regions, while allowing the most energetic particles to penetrate anywhere on the planet's surface. The magnetic field strength has varied significantly throughout geological history, creating periods of enhanced cosmic ray penetration during times of reduced field intensity. Magnetic reversals correlate with elevated extinction rates, suggesting that loss of cosmic ray shielding creates biological stress that affects ecosystem stability. High-energy cosmic ray particles originate from the most violent stellar deaths, carrying energy signatures that reveal their supernova origins. A 2025 study in the Astrophysical Journal proposes that massive stars undergoing gravitational collapse create black holes that generate powerful jets capable of accelerating particles to extreme energies. These jets interact with stellar material, to produce the highest energy cosmic rays detected at Earth, creating direct connections between distant stellar explosions and local biological processes. The particle showers generated by cosmic ray interactions distribute muons, electrons, and other secondary particles throughout Earth's atmosphere and surface environments. These secondary particles penetrate biological tissues and contribute additional sources of genetic variation beyond the primary cosmic ray impacts. The cascade effects mean that single stellar explosion events can influence biological evolution through multiple pathways operating simultaneously across different environmental zones. Cosmic rays represent active agents of evolutionary change rather than passive environmental factors, creating ongoing connections between stellar death events and biological innovation that span the entire history of life on our planet. These high-energy messengers from distant stellar explosions continue their influence beyond direct biological effects, fundamentally altering the atmospheric conditions that determine our planet's climate and habitability. Stellar feedback and atmospheric chemistry. These atmospheric transformations operate through mechanisms that connect stellar death events directly to Earth's weather systems and climate patterns. Variations in cosmic ray flux create measurable changes in global cloud cover that correlate with long-term climate patterns throughout Earth's geological history. Ice core data from Greenland and Antarctica preserve records of atmospheric conditions spanning 800,000 years. During periods of enhanced cosmic ray bombardment, cloud formation increased dramatically across both polar and tropical regions. The resulting changes in solar radiation reflection altered global temperature patterns and precipitation cycles on timescales ranging from decades to millennia. The mechanism operates through cosmic ray modulation of the global electrical circuit that connects Earth's surface to the ionosphere through atmospheric conductivity changes. Cosmic ray ionization creates conductive pathways that allow electrical charge to flow between different atmospheric layers. Variations in cosmic ray intensity alter this conductivity, changing the electrical field strengths that influence cloud droplet coalescence and precipitation formation. The process creates feedback loops where cosmic ray variations drive atmospheric electrical changes that affect weather patterns across entire continents. Lightning formation depends heavily on cosmic ray ionization to create the initial charge separation necessary for electrical discharge between clouds and ground. High-energy particles from stellar explosions provide the ionization pathways that enable electrical breakdown in atmospheric gases. Regions experiencing higher cosmic ray flux show increased lightning frequency and intensity compared to areas with reduced particle bombardment. The correlation demonstrates direct connections between distant supernova explosions and local weather phenomena that affect agricultural productivity and ecosystem dynamics. Stellar winds from nearby massive stars contribute additional atmospheric influences beyond cosmic ray effects by interacting directly with planetary magnetic fields and upper atmospheric layers. These particle streams carry charged material expelled from stellar surfaces at velocities exceeding 1,000 kilometers per second. When stellar winds encounter Earth's magnetosphere, they can either compress the magnetic field and reduce cosmic ray penetration or create gaps that allow enhanced particle bombardment of polar atmospheric regions. The interaction between stellar winds and planetary atmospheres varies dramatically based on stellar type and evolutionary stage. Young hot stars emit intense particle streams that can strip atmospheric gases from nearby planets through erosive processes. Older, cooler stars produce gentler winds that enhance atmospheric chemistry by providing additional ionization sources without causing atmospheric loss. The balance determines whether stellar influence supports or inhibits the atmospheric conditions necessary for biological processes. Cosmic ray-induced atmospheric reactions create complex organic molecules through pathways that mirror interstellar chemistry processes. High-energy particles break apart simple atmospheric gases like carbon dioxide, nitrogen, and water vapor into reactive fragments that recombine into larger molecular structures. Laboratory experiments show that cosmic ray bombardment of simulated planetary atmospheres produces amino acids, fatty acids, and other organic compounds identical to those found in meteorites and cometary samples. The organic synthesis occurs through radical chain reactions initiated by cosmic ray ionization of atmospheric molecules. Nitrogen atoms freed from molecular nitrogen react with carbon-containing fragments to form hydrogen cyanide and other nitriles that serve as precursors to amino acids. Oxygen radicals interact with hydrocarbon fragments to create aldehydes and alcohols that participate in sugar formation pathways. These reactions proceed continuously in Earth's upper atmosphere, creating a steady rain of organic compounds that contribute to surface chemistry. Evidence demonstrates that cosmic ray exposure varies systematically with galactic position, creating predictable cycles in planetary climate systems over astronomical timescales. Our solar system experiences enhanced cosmic ray bombardment when passing through spiral arms where recent supernova activity enriches the local particle environment. The galactic orbit period of 225 million years creates regular variations in cosmic ray intensity that correlate with major climate transitions preserved in geological records. The spiral arm passages expose Earth to cosmic ray intensities 30 to 50% higher than average interarm values. These enhanced particle fluxes increase cloud formation rates and atmospheric ionization levels across the entire planet. Climate modeling shows that spiral arm transits trigger ice age cycles through changes in cloud cover that reduce solar energy absorption at Earth's surface. The process operates over timescales spanning millions of years as our solar system completes its galactic orbital journey. Studies published in 2025 reveal that cosmic rays influence aerosol formation processes that regulate global temperature through complex atmospheric chemistry networks. High-energy particles create hydroxyl radicals that oxidize organic vapors released by vegetation and marine organisms. The oxidation products condense into submicron particles that scatter incoming solar radiation and modify cloud optical properties. Variations in cosmic ray flux alter aerosol production rates and atmospheric residence times, creating climate feedback mechanisms that amplify or dampen temperature changes. The aerosol formation process involves cosmic ray production of oxidizing agents that convert biogenic organic compounds into low-volatility products capable of forming atmospheric particles. Terpenes emitted by forests react with cosmic ray-generated hydroxyl radicals to create secondary organic aerosols that influence regional climate patterns. Marine-derived organic compounds undergo similar oxidation processes that affect cloud formation over ocean regions. These biological cosmic ray interactions create links between stellar activity and terrestrial ecosystem processes that operate continuously throughout planetary atmospheric evolution. Stellar processes maintain continuous influence over atmospheric conditions necessary for life through mechanisms that operate across multiple timescales from seconds to geological epochs. The recognition that stellar explosions, stellar winds, and cosmic ray bombardment directly control cloud formation, lightning patterns, and atmospheric chemistry demonstrates that life on Earth develops within an active stellar environment rather than isolated planetary conditions. Yet among all the elements that stellar processes deliver to planetary surfaces, one proves so difficult to manufacture that its scarcity creates fundamental limits on biological complexity throughout the universe. The phosphorus problem and stellar solutions. Phosphorus represents the scarcest essential element for biological processes throughout the known universe. Every strand of DNA contains phosphorus atoms that link genetic information together in double helix structures. RNA molecules require phosphorus to carry genetic instructions from cell nuclei to protein manufacturing sites. ATP molecules store cellular energy through phosphorus bonds that power every biological reaction from muscle contraction to neural transmission. Without phosphorus, none of these fundamental life processes can exist. The Atacama Desert stretches across northern Chile as the driest place on Earth, where rainfall occurs so rarely that some weather stations have never recorded precipitation. This extreme environment mirrors the conditions astronomers study in space, making it the perfect location for observatories that search for the rarest processes in the universe. Here, the ALMA radio telescope array points toward distant stellar explosions, where phosphorus forms through nuclear reactions so specific that they occur in only a tiny fraction of dying stars. The 2025 research conducted through ALMA observations reveals that phosphorus production requires extraordinarily specific stellar conditions that occur only during the final moments of massive star evolution. Stars between 15 and 25 times the mass of our Sun reach core temperatures exceeding 3 billion degrees during their death throes. At these extreme temperatures, silicon nuclei undergo rapid fusion processes that last mere seconds before gravitational collapse begins. During this brief window, silicon burning creates phosphorus through nuclear pathways that cannot occur under any other natural conditions. The nuclear physics behind phosphorus formation explains why this element remains so rare compared to other biological components like carbon, nitrogen, and oxygen. Silicon burning proceeds through alpha particle capture processes, where silicon-28 nuclei absorb helium-4 nuclei in rapid succession. The reaction pathway leads through sulfur-32 and argon-36 before reaching calcium-40. Phosphorus-31 forms as an intermediate product when calcium-40 undergoes proton capture followed by alpha particle emission. This complex sequence requires precise temperature and density conditions maintained for only seconds during stellar core collapse. The narrow mass range of phosphorus-producing stars creates severe bottlenecks for biological element distribution throughout galactic evolution. Stars below 15 solar masses never reach the core temperatures needed for phosphorus synthesis. Stars above 25 solar masses collapse directly into black holes without distributing their manufactured elements through supernova explosions. Only stars within this specific mass range contribute phosphorus to the interstellar medium through successful supernova events that disperse their nuclear products across space. Galactic chemical evolution models show that phosphorus abundance varies by factors of 10 across different regions of the Milky Way. The inner galaxy contains higher concentrations because massive star formation rates remain elevated in central regions, where gas densities support the formation of stars large enough to produce phosphorus. Outer galactic regions show phosphorus deficiencies that limit the chemical complexity available for biological processes on planets forming in those areas. The timing of phosphorus-producing supernovae throughout cosmic history determine when complex life could emerge on Earth. Geological evidence shows that phosphorus became available in Earth's oceans approximately 4 billion years ago through asteroid and comet impacts that delivered supernova process material to our planet's surface. This timing coincides with the earliest evidence for complex organic chemistry in ancient rock formations. The delay between Earth's formation and phosphorus delivery suggests that complex biochemistry required billions of years of stellar processing before sufficient quantities became available. When phosphorus-producing stars explode as supernovae, they distribute their manufactured elements across vast distances through shockwaves that travel at velocities exceeding 10,000 kilometers per second. These explosions inject phosphorus-rich material into surrounding molecular clouds where future star formation occurs. Computer simulations show that supernova-distributed phosphorus travels hundreds of light years before becoming incorporated into new stellar nurseries. The process creates expanding zones of phosphorus enrichment that gradually increase the chemical complexity available for planetary system formation. The phosphorus bottleneck may fundamentally limit where life can develop throughout the observable universe. Galaxies with low star formation rates or inefficient heavy element mixing show reduced phosphorus abundances that constrain biological chemistry. Dwarf galaxies often lack sufficient massive star populations to generate adequate phosphorus supplies for widespread life development. Even within the Milky Way, regions more than 50,000 light-years from the galactic center contain insufficient phosphorus to support the complex biochemistry required for DNA-based life. Isotope analysis of phosphorus-bearing minerals in meteorites provides direct evidence for the supernova origins of biological phosphorus. Primitive meteorites contain phosphorus with isotopic signatures consistent with explosive nucleosynthesis in massive stellar cores. The isotope ratios match theoretical predictions for phosphorus production during silicon burning phases that occur immediately before core collapse. These measurements confirm that the phosphorus in our bodies originated in stellar explosions that occurred within our galactic neighborhood billions of years ago. The discovery that phosphorus production requires such specific stellar conditions fundamentally changes our understanding of life's cosmic rarity. Complex biological chemistry depends not just on the presence of heavy elements, but on their availability in precise ratios that reflect billions of years of stellar nucleosynthesis. The phosphorus requirement creates an additional filter that restricts where life can develop beyond the traditional habitable zone considerations of temperature and liquid water availability. Every phosphorus atom in your body represents the product of stellar nuclear reactions so rare and brief that they occur in less than 1% of dying stars throughout the universe. The existence of genetic codes, protein synthesis, and energy storage systems depends on these exceptional stellar events that created the chemical foundation for all terrestrial biology. Without phosphorus-producing supernovae occurring at the right times and places, the complex chemistry that enables consciousness would remain impossible throughout cosmic evolution. The stellar influence on life extends far beyond the creation of essential elements. The same explosive events that forged phosphorus continue to shape biological evolution through ongoing processes that will determine life's future throughout cosmic time. Understanding these connections requires monitoring the stellar environment surrounding our solar system to predict how changing cosmic conditions will influence biological processes over millions of years ahead. Future stellar influence and life's cosmic destiny. Monitoring systems across the globe track these stellar changes with unprecedented precision. At observatories scattered worldwide, astronomers maintain constant vigil over the stellar neighborhood surrounding our solar system. The European Southern Observatory in Chile operates automated survey programs that monitor the brightness and spectral properties of nearby stars every night. These facilities track stellar activity patterns within a sphere extending 200 light-years from Earth, searching for signs of impending explosive events that could dramatically alter our planet's future. Survey programs completed throughout 2025 have cataloged over 50 massive stars within our galactic vicinity that will explode as supernovae within the next 10 million years. These stellar giants currently show spectroscopic signatures indicating advanced nuclear burning stages that precede core collapse. The most prominent example stands visible in our winter sky. Betelgeuse, located 600 light-years away in the constellation Orion, exhibits irregular pulsations and surface temperature variations that suggest imminent evolutionary changes on astronomical timescales. This red supergiant star has entered the final phases of stellar evolution, where silicon burning occurs in its core. Spectroscopic observations reveal that Betelgeuse has already exhausted its hydrogen and helium fuel supplies, progressing through successive nuclear burning stages that create increasingly heavy elements. The star's irregular brightness variations and dramatic size changes indicate internal instabilities that precede core collapse. When Betelgeuse eventually explodes, it will become visible during daylight hours and remain the brightest object in our night sky for several months. The cosmic ray environment surrounding our solar system will change dramatically when nearby stars like Betelgeuse reach their explosive endpoints. Supernova explosions within 600 light-years of Earth can increase cosmic ray bombardment by factors of 100 times current levels. These enhanced particle fluxes will penetrate Earth's atmosphere and reach ground level with sufficient intensity to affect biological systems directly. Climate models predict that such events would trigger atmospheric chemistry changes, leading to ozone depletion and increased surface ultraviolet radiation. Our solar system's orbital motion through the Milky Way galaxy exposes Earth to varying stellar influences over timescales spanning millions to hundreds of millions of years. The galactic orbit carries us through different regions containing distinct stellar populations and cosmic ray environments. Computer models tracking our future galactic trajectory show that we will encounter several massive star-forming complexes over the next 50 million years. These regions contain numerous supernova candidates that will explode as we pass nearby, creating episodes of enhanced cosmic ray bombardment. The Orion Arm, our current location within the galactic spiral structure, will experience increased star formation activity as gravitational interactions compress local gas clouds over the coming epochs. New massive stars forming within our stellar neighborhood will eventually explode as supernovae, adding to the cosmic ray environment while distributing fresh heavy elements throughout local space. The cycling between star formation, stellar evolution, and explosive death creates predictable patterns of cosmic ray variation that life on Earth must navigate throughout future geological periods. Research published in 2025 reveals that nearby star formation regions already influence our cosmic ray environment through mechanisms beyond supernova explosions. Young stellar associations emit powerful stellar winds that interact with local interstellar magnetic fields, creating turbulent regions where cosmic ray particles become trapped and accelerated. The Scorpius-Centaurus Association, located just 400 light-years away, generates cosmic ray acceleration zones that contribute measurably to the particle flux reaching Earth's atmosphere. When massive stars in our vicinity eventually die, their explosive deaths will reshape the local interstellar environment in ways that affect planetary habitability throughout our galactic region. Supernova shockwaves compress surrounding gas clouds, triggering new episodes of star formation while simultaneously clearing vast cavities in the interstellar medium. These processes create complex feedback loops where stellar death events influence the formation of subsequent stellar generations that will determine future cosmic ray environments. Studies examining stellar feedback effects on galactic habitability demonstrate that star formation and stellar death processes determine where life can persist over cosmic timescales. Galaxies with high supernova rates experience cosmic ray environments too intense for complex biological development. Galaxies with insufficient massive star populations lack the heavy element production needed for terrestrial planet formation. The Milky Way occupies a middle ground where stellar feedback creates challenging but manageable conditions for biological evolution. Galactic evolution models incorporating stellar feedback mechanisms show that habitable conditions change continuously as galaxies age and their stellar populations evolve. Early galaxies contained primarily massive stars that exploded frequently, creating cosmic ray environments hostile to life development. Modern galaxies like the Milky Way contain more diverse stellar populations that produce manageable cosmic ray levels, while maintaining heavy element production necessary for planetary chemistry. The future habitability of our galactic region depends on the balance between star formation rates and supernova frequencies over the coming billion years. Current star formation models predict that massive star production will decline as available gas supplies become depleted, reducing future supernova rates and cosmic ray generation. This evolution toward lower cosmic ray environments might favor the long-term stability of complex biological systems, while simultaneously reducing the mutation rates that drive evolutionary innovation. Our cosmic future remains intimately connected to stellar life cycles through mechanisms that operate across multiple timescales, from individual stellar lifetimes to galactic evolution epochs. The massive stars currently visible in our night sky will explode within the next few million years, dramatically altering the cosmic ray environment that shapes biological evolution on Earth. Understanding these connections allows us to anticipate the cosmic influences that will shape life's development throughout future geological periods. The stellar processes that created the elements in our bodies continue operating throughout the galaxy, manufacturing the heavy elements needed for planet formation, while generating the cosmic ray environments that drive biological change. Life on Earth will continue adapting to changing cosmic conditions while remaining fundamentally connected to stellar processes that began before our planet formed and will continue long after our sun exhausts its nuclear fuel. These discoveries reveal connections between distant stellar events and terrestrial biology that extend far beyond what anyone previously imagined. The stellar origins of our atoms fundamentally shape every aspect of life on Earth. The carbon forming your DNA backbone condensed in ancient red giant cores billions of years ago. The oxygen powering your cellular respiration crystallized during massive stellar explosions that scattered heavy elements across our galactic neighborhood. The phosphorus enabling your thoughts to occur formed during the final seconds of dying stars through nuclear processes, so rare they happen in less than 1% of stellar deaths. These atomic inheritances connect every biological process to specific stellar events that occurred throughout cosmic history. When you look up at the night sky tonight, you witness the ongoing stellar processes that created you and continue shaping life throughout the universe.